Okay, well, I think we could start. So welcome to the next, I think, 5th plenary talk of JSALT. And today I have the great pleasure to welcome Hervé Bredin from France. So Hervé did his master's and PhD with the school or the University of Telecom in Paris. Then he spent some time in Dublin, in Ireland. And then basically it's the French academic or research career with the CNRS, with the French network of research institutes in Toulouse, in Orsay with LIMSI, and now Listen. Then again in Toulouse. Hervé was also consulting, but I think nowadays he's the most known as the pyannote guy. So pyannote started as an open source project, right? But it developed into a startup company where Hervé is the co-founder and CSO, Chief Scientific Officer. And well, I think that's where I will stop, and I will pass it over to Hervé, and thanks for being with us.
Yeah, thanks a lot for the introduction and for the yeah, thanks for the opportunity to give a talk here in front of all of you, la crème de la crème, as I usually call you when I talked about you guys to my family. So they are actually there. So I wanted to say hi to on the camera. I mean, my two sons, Adam and Noé. Hello. So yes, this is basically a talk that I already gave 2 months ago, because I was just told a few days ago that I should give this talk today. So I apologize for those of you who may have attended the previous talk. Those are the same slides. So yeah, a quick word about me, but everything has been said already. So I've been a tenured CNRS researcher since 2008. And started working on speaker diarization a bit more than 12 years ago now, and focused almost exclusively on this problem that I really love. Yeah, back in 2015, I started actually open sourcing Pyannote as a way for me to make my research reproducible. First, it was really the main idea, because papers are kind of useless if you can't reproduce the results. That's what I think. And so I systematically put all the new results in this Pyannote toolkit. So it grew with me and my research. And apparently it became quite popular. So those are just on the right here, a few numbers that gives you an idea of the popularity of the toolkit. GitHub stars, this is a red line, Pyannote is the red line, and also the pre-trained neural networks that are shared on the Hugging Face platform. If you saw the models tagged with the audio tag on Hugging Face, the top 5 are actually from Pyannote in terms of number of downloads, whatever that means. And so based on all of this and the fact that I really liked building tools that people are actually using and doing stuff with it, even non-experts, I actually co-founded pyannoteAI, so a company around the open source toolkit, but we also have obviously other products that are not open source. And so I'm currently on leave from CNRS since March. So it's only been a few months that I've been focusing almost exclusively on the company. So please do interrupt me whenever you feel like it. So I apologize for those of you who actually know the answer to this question. But so what is speaker diarization? I'm going to spend a bit of time on this. Speaker diarization falls under the umbrella term of speaker recognition, so speaker recognition task. I wanted to highlight a few of them before really diving into what speaker diarization is, so that you can really understand what the specificities of speaker diarization are compared to speaker verification, for instance. So speaker verification, I summarize it as a supervised task, in the sense that we do have access to enrollment data of the speakers that you want to recognize. So it is supervised by some training data here related to the speaker. And it's a binary classification, because the question that is asked is answered by a yes or no. So the question is basically, given an audio recording, is this speaker A actually speaking in this recording? There's an extension of speaker verification, which is speaker identification, where you increase the number of classes and you have to decide which speaker is speaking among the speaker in the training set. Now we're getting a bit closer to speaker diarization with a thing that I called speaker tracking, but it's also being called now target speaker VAD, target speaker voice activity detection, for instance, where the idea is to decide where a given speaker, detect when a given speaker speaks in a recording, potentially with multiple speakers in it. And now we come to what really speaker diarization is. So we usually sum it up as the who speaks when task. So it differs from the other task in the sense that it's unsupervised. Unsupervised in the sense that we have no idea beforehand I mean, we might have never heard the speakers involved in the conversation to actually track them in speaker diarization. So it's unsupervised in that sense. You'll see later that we do train speaker diarization neural networks in a supervised manner, but with respect to the actual identity of the speaker, it's unsupervised. We don't know who might be there. We might even never heard them before. And so it's basically a decision that you have to take every frame, and it's analog to a clustering task in the sense that I'm going to, the color here in those frames do not matter. It could even be green, blue, and cyan here. We could just mix up the green and blue. It would still be correct. It's really the actual, not the actual identity of the speaker that matters, but the fact that two speech turns of the same speaker is always tagged with the same label. But we could call them apple, banana, and orange, or A, B, and C. It doesn't matter. So there are many variants of speaker diarization, obviously. I'm mostly going to talk about the two first one in this talk. So what I call batch speaker diarization is when you have access to the whole recording of a conversation before processing it, while streaming, obviously, you process it in real time with a variable latency, but basically you need to take the decision as the conversation unfolds. And there are another type of task, which I call the longitudinal speaker diarization, where you have to track the same speaker across a large collections of recordings. So usually, speaker diarization is not the final goal. There are some tasks where speaker diarization is very close to the final goal that we want to achieve. But in practice, it's usually in a scenario where you want actually to attribute a speaker to a transcript. So that's the main use case. That's the kind of use case that we see now in the pyannoteAI company. So our customers would, for instance, use speaker diarization first, then transcribe, and then on top of that, apply LLMs to, for instance, summarize a meeting or make the list of action points of who promised what to do for the next meeting. And it's also, speaker diarization is also being used to help training a voice agent or voice assistant. Basically, those voice agents actually need very large training data set to be trained. And companies like Qtai are using Pyannote to first clean their training data set, segment into speakers, and this allows them to have better model down the line during training. It can be used for text-to-speech training to prepare the training set with only single speaker segments. Because otherwise, if in your training set there is, for instance, lots of overlap, you might have artifacts in the voice clones. Then we've been told many times that if it's not by customers, I mean that if it's not clean, basically it's garbage in, garbage out. And sometimes we've been told that voice clone of a male would end up with small laugh or back channels of a woman in the synthesis, while it shouldn't be. And it was because of bad training data with overlapping speech in the training data. And yeah, it's being used for other tasks like automatic video translation, so that you actually put the right voice to the right speaker when you generate video in another language. And also, for instance, it's being critical for live logging applications where you don't want to record anyone unless they gave their permission to be recorded. So for that, you need to track the speakers. And yeah, I just wanted to highlight that actually the popularity of speaker diarization really grew when, I mean, from my point of view, and popularity of pyannote really grew when Whisper came out, because so it kind of commoditized the transcription in some way, but it didn't give speaker labels, so people turned to pyannote to make a combination of the two. So why are we still working on this, and why are we 20 people in the EMA team to work on this, and why isn't it still solved? So there are many reasons why that is the case, but I've put some of them here. So we have to actually handle very short speech turns. We are not allowed to miss them, obviously. They are much more difficult to assign to the right speaker when they're small. There might be a lot of overlapping speech. This is an example of the AMI dataset where at some point there are even 4 speakers speaking together, and the overlapping speech account for 40% of the speaking time. And yeah, one of the main problem or difficulty as well is the fact that we don't know in advance the number of speakers. So this makes the problem a bit different than the other one. It's more like a clustering task than a regular classification task. And another problem is that you might have unbalanced speaker time between the speakers, which makes the clustering also a bit more difficult. So I have a few slides really to summarize how it was done before, how it is done now, and what is the evolution of the speaker diarization system. It's very high level, so don't expect too much details here, but historically it was more like a cascading approach. So you would first start with speech activity detection. So given the audio recording, you would first extract all the speech regions. And then within those speech regions, you would split into speech turns. So basically processing speaker change detection. So you end up with lots of small segments, but where supposedly there's only one speaker speaking in each of those segments. And then we would extract speaker embeddings from each segment. And those are represented here in 2 dimensions, but you obviously know that it is a much larger dimension that we have nowadays. And then simply doing clustering in this space, and then reassign the speaker label to each speech turn accordingly. And here the output shows some kind of overlapping regions, which obviously were not here. So what is missing in this picture is that there was also some modules of just focusing on overlapping speech detection to actually add those segments. Another trend, the trend is to actually forget about all those steps and do that all at once. People in the EMA group are, and I'm one of them, are struggling those days to actually make it work, especially for very long sequences and a large number of speakers. So the idea here is basically to train a neural net with audio as input, and the output are directly the speaker probabilities. So here you would have a model trained to output up to 3 speakers, but it detected that only 2 are active, the green one and the orange one. And basically, we're training the model to output this kind of stuff. So by design, though they are work that try to generalize to a larger number of speakers and even a variable number of speakers, by design, most of them have a fixed number of speakers. So they usually, this is usually a maximum, an upper bound number of speakers that they can actually detect. And what's nice with these kind of approaches is that it's overlap aware by design. If 2 speakers are active at the same time, then there's no issue here with this kind of approach. So let me quickly summarize the pros and cons of those 2 different family of approaches. So The multi-stage diarization, the first slide, was it's basically a cascading approach. So you would have multiple modules. If one of them makes some mistakes, you can't recover. So that's an issue. And as I said, it can hardly handle overlapping speech. While on the other side, those two problems are not there because there's no propagation of errors, because there's only one module. It might be not that great, but still. And the overlap is handled from the start. And so now the other way around, the end-to-end neural diarization do have some cons, like it's difficult to train them. It is. So it's not so good at generalizing to a previously unseen number of speakers, especially larger number of speakers that it has seen during training. And it's hard to make them scale with the duration of the file, while the other approach doesn't have those problems, or not so much. So the idea, and what the idea is to try to take the best of both worlds, and this is what the community called the EEND-VC family. So EEND is for end-to-end neural diarization, and VC for vector clustering. So the idea is to try to combine the two approaches. This is a quick description of how it works within pyannote. There are variants in the literature, but yes, I obviously know this part a bit better. So how does it work? So let's say you have a 1 hour long audio file. We would simply slide, let's say, a 20-second window on this recording with a bit of overlap between the two. So here, each of those rectangles are actually 20-second chunks. And you see there are like 50% overlap between the two. And the idea is first to apply a neural net that does end-to-end but local speaker diarization on those chunks, separately from each other. So for instance, for the triangle chunk, we get this diarization. So there are 2 speakers in there. For the circle chunk, we also get 2 speakers, and for the star, we also get 2 speakers. But you see that those 2 speech turns are actually from the same speaker, but not necessarily contiguous. The problem at this point is that we have no idea of what triangle corresponds to what circle, so we rely on a speaker embedding and clustering step to actually merge all those speech turns. So each of those speakers in these segments are actually represented as a point here in this space. We apply agglomerative hierarchical clustering there. And this is where actually we can detect more than the, let's say, 2 or 3 speakers that can be detected locally. Because clustering can adapt and detect more speakers. And once we have assigned each segments here to a cluster, we can simply stitch them back together to build the final diarization. And that's what pyannote is doing right now, and a bunch of other systems. Maybe I can stop here for questions before I dive into a selection of papers that I've. Yes, Luca, maybe?
What does it mean to
yeah.
Just a moment.
Thanks. You showed a graph with speaker probabilities. What does it mean? Like, is it? I was thinking maybe it's either one speaker is talking or not. What does it mean to have a 33% of probability of speaking?
Yeah. You mean here, the probability here?
Yeah.
No, this is basically the output of the model. Indeed, we train them to say either 0 or 1, but the predictions are actually continuous between the two. So the higher the number, the more likely the speaker is active.
And so can you interpret, like, is there any interpretation when you have the model is uncertain regarding whether a speaker speaks or not? Is it because there is confusion between 2 close speakers? Or?
Yeah, it could be because of confusion, or it could be because of it's not even sure that there is actually speech or not because of background noise, or yeah, those 2 reasons might explain why it ends up, yeah. Yeah, there was.
You mentioned two approaches. Are the accuracies about the same in the two approaches? You didn't mention, yeah.
The accuracy are not the same, but also mostly depends on the type of audio you process. For instance, if you know that there are only two speakers in the conversation, it's probably best to go I mean, if you know in advance the number of speakers and it's a very low number, you're probably better off going the full end-to-end way, because the problem is maybe easier to solve, but when you have to predict the number of speakers in advance, the approach with a cascade and the clustering step is probably more reliable and might generalize better to different numbers. So there's no silver bullet for now that we
Are there sort of established benchmarks and data sets and standards?
Yeah. Lots of them, yeah. The community has been very active in terms of organizing benchmarks. I can cite Diehard. There was this Displace challenge as well, where diarization in Hindi and English. So it's been very active. There are not that many active benchmarks right now in terms of diarization, I think. Because Diehard kind of ended, Vox SRC kind of ended as well, but so lots of data sets that we can compare. Yeah. I wait for the.
Just a quick question. You said fixed maximum number. What is a reasonable maximum number? Because I think you might still suffer from the same problem for the local end-to-end speaker diarization.
So what I usually do, and what people usually do, is you would actually slide this window on the training set to actually count the number of speakers, the distribution that you can expect in like 20 seconds. And on all the benchmark that we were talking about, it's rare that there are more than 5 speakers. So I mean, for this kind of duration, like 20 seconds, 5 speakers is more than enough to cover like 99. I hope it won't break the streaming. So you can actually assume that this number is kind of low for locally. Yeah.
Oh, okay. A few seconds means 20 seconds? Because I had a different definition for fewer in that context. I thought it would be shorter.
Shorter than?
You said a few seconds sliding window, and you said 20 seconds. So I thought it might be just 2 or 3 seconds or something.
No, it's much longer. Otherwise, you can't really do diarization within, because usually there will be just 1 speaker or 2 at most. And
in 20 seconds, you might have a lot of speakers.
Okay. So now comes the only joke of my talk. Like I turn love into loss, because I realized that what I've been working on mostly in the past few years is really focusing on how to design loss functions to address the speaker diarization task in an end-to-end neural manner. And so I wanted to talk about the 3 papers, but I'll probably talk just about the first 2 ones, because I won't have time for the third one. So these are collaboration with former students of mine. The first one will be about the powerset loss. The second one about how to extend this kind of loss to the streaming scenario. And there was this one that I probably won't have time to talk about. It's basically how to extend speaker diarization and to speaker separation and train them jointly. So the first one. So historically, the end-to-end neural diarization approach would model a conversation with these 0 and 1s. So basically, we would train neural network. So given, let's say, 20 seconds here, let's assume this is a 20-second chunks of a conversation between 2 people, Alice, Bob, and Carol. We would train a neural network to actually output this kind of binary representation. So basically for each frame, so a time step t here could represent like 20 milliseconds, 50 milliseconds. So every 50 milliseconds, you would have to decide whether speaker 1 is active, speaker 2, or speaker 3 is active and output the numbers corresponding. And so we would train a neural network to take as input the raw waveform most of the time, or filter banks basically, and then it would output this kind of output. So those are, the darker is the higher the value is, and the lighter the smaller it is. And then we would simply compute the binary cross-entropy between this prediction and that one. And so we trained the model like that, and at inference time, we would need to put some kind of threshold on those binary score to decide, let's put it at this gray level, for instance. If the threshold is at this gray level, then anything darker than this would end up in a 1 here. And so that's basically how the first neural diarization models were trained. What you have to keep in mind is that since diarization is a clustering task rather than an actual identification task, any permutation of the output would be correct as well. So those 3 different permutations are actually the same diarization. We simply permutate a few speakers. So the loss function needs to be robust to this. And this is what we call permutation invariance learning. So basically, instead of computing simply the binary cross-entropy between the prediction of the model and the target, we would minimize over the whole set of permutations of the prediction or the target. By the way, we can permutate anyone we want. And so that makes this speaker diarization problem a bit trickier, because 2 completely different outputs could be as good as each other. So this is different to many other classification tasks where this never happens. And so the proposal of Alexis in his paper has nothing to do with this permutation invariant problem, but I wanted to highlight that anyway. It is more related to the fact that we need this threshold here, which tends to be kind of sensitive. And so what Alexis proposed is basically to formulate the problem in a different manner. Instead of having 3 classes, 1 for each speaker, you would have 1 class per each subset of speakers. So the first class would be no speaker at all, so that's basically a VAD. It's either non-speech, or if it's not that, it means that someone is speaking. And one class per each speaker on their own, and then all possible pairs of speakers. And you see that I'm probably missing here the subset that contains 3 speakers. And this is the same as the same reason as when I answer your question. It's because it's very unlikely in actual data that there are 3 speakers, and so we decide not to use this class, but we could add it as well. So what makes this formulation different from the multi-label one is that also now the classes are mutually exclusive. So usually lots of training algorithm optimizers are more, I think, suitable or more adapted to this, just because this is a standard classification problem. And we no longer need to have a threshold to decide whether each speaker is active. We simply take the class that is the most likely. And also, we might actually use this thing to be able to control a bit more the VAD, the voice activity detection aggressiveness, though I've never really worked on this. So quick results of the switching from the multi-label approach to the powerset multi-class approach on the Diard dataset. So the Diard benchmark is one of the dataset that I mentioned earlier in my answers. So these are diarization error rate. For those of you who don't know, so the diarization error rate is the sum of 3 error rates. So false alarm, when you detect speech when there shouldn't be speech. Misdetection is the other way around, including overlapping speech that you might have missed. If you detect only 1 speaker, but there are 2, it's considered misdetection as well in this metric. And speaker confusion, where you actually mix up speakers. And so this figure here shows the results of the same model trained with the 2 different losses. On the 2 first columns is this. The third one is about after being adapted to each data set, so don't worry about that one. But basically, how can you read this figure? So on the x-axis, you have the 11 application domains that are part of the Diard dataset. And it's a really nice dataset because you can actually use it to evaluate the generalization of your approach usually. That's what I tend to do. I tend to remove Diard from the training set and use Diard only as a test for how well models are generalizing. So let's take this domain, for instance. I think this is conversations between two people, a doctor and a patient. And you see that going from multi-label to powerset, we usually get better at miss and false alarm. And if you focus explicitly on the overlapping speech regions, we see that we are usually better at detecting overlapping speech. So basically, the amount of errors coming from the overlapping speech is reduced here. And it's mostly always the case if you carefully look at the area of this hatched region. So that's really the main improvement, I think, from this kind of approach, though lately it's not that obvious with new neural architecture that the powerset is actually better. At the time, it was way better. Now, the conclusion might differ a bit. And on some data set, it would be better to use multi-label, on others to use powerset. That's it for this part. Are there any questions?
How large are the individual data sets here? I mean, how big of error bars should we be thinking are on these word error rates? Like, are these statistically significant differences, or are they within the error caused by size?
I think they are around 10 to 12 files per domain maybe. I think in total it must be 230 files in total, split into all the domains, but the CTS one is much larger. This one is definitely statistically significant. The other one, a bit less maybe, yeah.
Okay, well, I have a second question, but I'll not hog the microphone. I'll ask later.
Go ahead. Yeah.
The permutation and variance stuff. So have you tried to do anything about this problem?
Do you mean solving it? Or I mean, the way of solving it is simply to iterate over. At some point, I tried to. So this definitely this mean is not differentiable. That's an issue. I don't know if that was your question behind.
Yeah.
So
Yeah.
back then in Montreal in 2019, my first JSALT, which I enjoyed so much that I came back here this year. I tried to actually do this permutation thing in a differentiable manner using sinkhorn loss and stuff like that. Never really managed to make it work, but probably because I realized that I really thought when I first thought about this problem of permutation that this would be an issue that it's not differentiable. But apparently it's not at all. It just works fine just by permutating and selecting the best permutation for the backward, the propagation of the gradient. Yeah.
I mean, doesn't the min get really big if you have a lot of speakers? Because you have...
Does it get big?
Well, you have factorially many orders if you're just going through all of them.
So in practice, we don't implement it like this. Well, what we start by doing is simply computing a 3x3 binary cross-entropy matrix between all possible speakers in the prediction and all possible speakers in the target, and you would simply use the Hungarian algorithm to find the matching, the one-to-one matching that minimize this. So you don't have to go over all the permutation in practice. So maybe it's not exactly equivalent, but it works just fine and it's fast. Yeah.
Got it. Makes sense.
Let me ask you something to clarify, because I know Ramani has a question after me. So when you talked about this powerset loss, you you didn't imply that the permutation problem is gone, right? Because you still have to choose what to call S1, S2, and S3.
No, it's not gone, yeah.
Yeah, so okay. So do you do the same thing? Just do all pairwise and figure out which
Yeah,
is
yeah,
the best
exactly.
match?
And by the way, for this permutation thing, we actually go back to the multi-label, find the optimal permutation in the multi-label space, and then go back to this, because we couldn't find an easy way to do that in the powerset space, yeah.
So does your stuff, do you have plans to add multi-channel audio or something like that? Because humans probably use spatial cues of some sort to diarize in their brains, kind of, right?
Personally, no, I don't plan to work on this, but people in the EMA group are working on this. And so yes, indeed, you can do GCC FAT information that you can add to this, and definitely, yeah.
Okay.
Yeah. There's a question over there.
Okay, in terms of these permutations and such, you solve basically this assignment the problem in the loss function, but still the model has to consistently decide for the whole recording if Michal, for example, should be person 1.
Yeah.
So do you have some idea how much confusion actually happens because the model in inference can't decide if the person should be which one, if S1 or S2?
I'm not sure I understand the question.
Okay,
How
so
I decide to put the speaker 1
yes, still
at
the model,
index 3 rather than 4, or?
Yeah, still the model, when it gets the recording, it has to decide, okay, this person should be S1.
Yeah.
In training, when you train it, you solve it in the loss function, but
Yeah.
the model has to consistently decide for the whole recording if this person should be S1 in the inference.
Yeah, so there have been some papers actually looking at the insides of the model, and you know, the models are big transformer, and you can actually look at the representation internally, and what you see is that it's progressively actually clustering the frame of the same speaker as you go deep in the model, but why it would decide one speaker to be assigned to that one rather than that one, it's another question that I think at some point I tried to study whether, for instance, that was the most talkative one who would end up first, and then they would be sorted in other, or at least that the most talkative one would always end up at the same index. That could be that would be an interesting analysis to do based on statistics on the interaction of the speaker, or whether, yeah, I don't know. Yeah, it's really not clear how it behaves internally and why it takes those decisions. Yeah. Okay. So let's switch to the second paper then. Okay, I need to. So that one was done with an undergrad, Bilal, who is no longer in the speech area. I went into the computer vision stuff after that. Probably it was because of me. I don't know. Let's see. So Bilal actually worked on streaming speaker diarization. So sorry, the slides was meant to have some animation, and not everything should appear at once, but that's the only slides that I could find. So I didn't really talk up to now about the architecture of the neural network that I've been using for the first paper. And so the one that I'm mostly using, or at least in this paper, were basically based on a bidirectional LSTM. So we would have first a filter banks. I went with the SyncNet trainable filter banks, but it could be fixed handcrafted filter banks. Then LSTM would process in the two direction each chunk the model, and then a final classification MLP we would really output this kind of prediction. The problem with this kind of model that we wanted to use it for streaming, but obviously it can't be used for streaming because it relied on bidirectional LSTM. So what we did, the first thing that we did is that we made them monodirectional, like just from left to right. And just by switching from bidirectional to unidirectional, the DER went from 17.3 to 20.3. So a huge increase in error rate. So then there was an issue as well on the feature extraction step, because there would be normalization along the time dimension. They would be centered or whitened based on the temporal dimension. So we couldn't do that either. So we removed the instance normalization, and once again, a decrease in performance. So the question of this work was really, how do we get closer to 17.3? How do we change the architecture, the loss function, something to actually go back to the performance of the offline model? So our way to do that was to allow the model to actually a bit of look ahead before taking a decision. So it would be allowed to wait a bit before taking its decision. So this is how we train the model without this look ahead. So basically, for each time step in the audio signal as input, the model will predict, so we call xt a frame, basically, of the audio, and it would predict y hat t, which is basically the probability of each speaker being active at this particular time step t. And then the loss function simply compares every single step to every single corresponding step in the target. So the idea here is very simple. We simply shift in the past the prediction. So how does it work? So basically, instead of predicting with a line time step, we would simply, at time xt, we would predict what happened lambda frames before. That's it. So that's a very common way of doing look ahead. And and then we simply compute the loss exactly the same way, except the first prediction are thrown away because they correspond to what happened before the beginning of the signal, so they are meaningless. And we also throw away the last few target frames because we have no predictions corresponding to it. But then the loss function is exactly the same, and we don't have to change anything. And what's nice with this approach is that we can actually do that for multiple latencies at once. Here, you have just one latency, but if you add many final classification layers with different latency, the same model can be trained with a 0-second latency, 1 second, 2 seconds. They share the same architecture, it's just the final layers that change. So that's very convenient. So that was the point of the paper by Bilal. And so he trained the model like that, and we got this kind of result. We did a study of the trade-off between the latency and the accuracy. And the right column here is always the performance of an offline model, so basically the bidirectional one that I mentioned earlier. And you see that obviously as the allowed look ahead or allowed latency increases, we get closer and closer to the performance of the offline performance. So this is for voice activity detection. So basically we use just the output of the segmentation model as a VAD, as a voice activity detector. So this is F-score, the higher, the larger. And we can do the same for overlapping speech detection. If the model outputs classes with 2 speakers, then it's overlap speech. And same, we get closer and closer to the offline. And also, we evaluated speaker chain detection. This is an error rate, so the lower, the better. And you can see that the confidence score are quite high here. I think it was on AMI, that one, and there are not that many files in the test set. And yeah, I think that's it for, oh yeah, now I have a demo of what it looks like in practice. We actually built on top of this since then at pyannoteAI, and I can play a short video showing how it works in practice. Yeah, I'll try. Is it open?
Yes.
We couldn't manage to. Let me put the sound. So at the top, you have here the reference of a conversation between two speakers. The middle is what you would get with a regular VAD. This one is at 80 milliseconds latency, I think. And this is what we call VAD on steroids. So it's basically using this segmentation model that I just described with, I think it was, on that one is 200 milliseconds latency. Let me play the video.
Your mother would say, now, pick up all your what?
Toys.
Just toys?
Yes, sir, toys.
Did you ever hear play pretty?
Play pretties, back yonder, yes, sir. They would mention that. Some of them would call them toys, cool. And then some of them call them play pretties. Get your play pretties and put them up.
Is that right?
Yes,
They were small.
oh, yes, sir.
So which one is it, the middle one? Okay. So what I wanted to show here is that it's not actual diarization in the sense that we can't track speaker in the long term with this kind of approach, but locally it's actually very good compared to what we can get with our best speaker diarization, batch speaker diarization so far. So you see that here, this green speaker should actually be yellow, but because it stopped speaking for a while, then the model can no longer track them. But it's actually in streaming, and there are many use cases where it can be useful, especially for translation of live streaming events. People who do voice cloning on the fly are happy with this kind of behavior because they can just restore their voice clone for every new speech turn that is detected. So that's already useful. The next step is obviously to go all the way down to speaker diarization. Yeah, I think that's it for the streaming part. And I'll probably, yeah.
Yeah, I have one quick question. So on the previous slide, I was wondering what happens at 500 milliseconds, because I think, is that something that changes in the data or at the model, or do you have any intuition? Because I think in every of these three plots, there is like a step at 500 milliseconds.
I don't know, it's just also that the step between all those increases here. It's not the same step between that one and that one and that one and that one. That might be just it. I don't know. Or maybe because speaker change detection in practice is kind of impossible maybe for 250 milliseconds delay. Or also it might be because of the actual annotation of the dataset. It cannot be precise. I think the DIAR dataset, the annotators were asked to be around that level of precision. I'm not completely sure about the details, but there are different conventions when annotating the dataset, and yeah, that might be the reason. You know, VAD, it goes up regularly. The more context you have, I guess, the easier. But for speaker chain detection, you really need at least a few more milliseconds to take the right decision. So by the way, those results were with a model that was trained with all the latency at once. You do one pass, and you get the prediction with 0 latency, 50 milliseconds latency, just in one pass. So that opens up maybe new applications, you know, like providing partials and finals in the prediction directly. Because we noticed that after 3 or 4 seconds latency, basically you get the performance of the offline thing. So your final after 4 seconds.
What are the error bars here?
So it's basically, I think it was just the 95. So we basically computed the VAD, on all the files in the data set and looked at the distribution of the error rate and took the 95% percentile or something like that. Okay. So that's why it's large, because the data set is kind of small in number of files.
And when you say after 3 or 4 seconds you get back the offline performance, does that include the consistent identities for the different speakers? Or
No, just the, let's say the segmentation part, and not the identity on the long term. No. we are not there yet. Yeah. Okay, I'll switch this. I just want to talk a bit about the pyannoteAI company, because that's who I am now. And yeah, basically a few words about the company. So we have this mission of democratizing seamless human interaction, grounded in scientific excellence. That's a really important thing for me. I come from the academic world, so we are building a research lab inside Pyannote, and we will keep publishing and as much as we can, and keep contributing to the community and benefit from it as well. I already learned so much in this first week that I spent here. And we are, so hiring, we are working on all things speaker related. So basically speaker diarization, speaker identification, separation, speaker attributed transcription, streaming speaker diarization, and also one thing that I would like to work on later, interactive speaker diarization, where you would have a human and a machine interact to get to a perfect speaker diarization as fast as possible without human intervention. So you would have a machine and a human interact for, let's say, there are applications where it's critical to have perfect diarization, and having a human in the loop is needed here. A few words about the resources that we have. So right now we are a few of us. Antoine is here, I don't know where, in the research lab. And we also have the chance to have access to a lot of compute. So we have access to the French supercomputer. It's very nice. Any French company actually with doing research in French can access this supercomputer. And yeah, this thing about money, which I'm not very comfortable talking about here, but still, we raised a lot of money and we can afford to hire people and buy data and make better diarization come true. And yeah, I had a few slides just showing that we're getting better and better at speaker diarization, and we keep pushing. And if you've been using the pyannote.audio open source, it's in light green here, and we are currently working to go down as fast as we can to the closest number we can get on those common benchmarks that I discussed earlier. And we also are working a bit on the speaker attributed transcription stuff, because we have actually lots of people coming to us that they are using WhisperX, for those of you who don't know, and they are not happy with that, so we're trying to build on top of that and provide ways of improving the attribution of the speaker to the transcript. We're not working on transcription ourselves, but we try to make the integration easier. And yeah, I think that's it for me, and yeah, thank you very much.
Okay, I had 2 or 3 questions. One of them has to do with what you consider a speaker in diarization. So do your customers, or do you ever think about playback audio? If there is a loudspeaker in the room playing some audio like a radio, is that a speaker, or is that to be ignored, or it's special and not a speaker, but still?
We are not asked a lot for now about this, like even extracting different characteristics of speaker, I don't know, age, gender, or whether it's replayed audio or not. Mostly, yeah. Right now, no, we didn't really work on this particular topic. We do think about what is speech and what is not. So sometimes we have customers asking us to detect, obviously, laugh, cough, and everything that is non-speech vocalization, stuff like that. So this is something that we're working on as well, to make the information available to what they are going to do next with this as complete as possible. Yeah. So, but yeah.
Can you say a bit more? I mean, for example, laughter, is that as easy or hard as speech, or harder or easier?
Is it harder or easier?
Yeah.
We are just getting started actually on this particular part, and it's not clear what they want to do next as well with this. So we need to build this with the customers to really understand what they want it for. But We probably won't diarize laughs. Detecting them is one thing already. Yeah. And they're using it to have an idea of how well a meeting is going. And same for overlapping speech detection. They would use this as clues as whether a call is going well or not, or this kind of stuff.
Yeah, laughter is known to be quite important in studying group dynamics, so yes. Yeah. So the other two questions I had to do with evaluation. Yeah. I think you mentioned DER many times. Yeah. But, we've talked about this many times over. So what really matters in the commercial world? Is it enough to just reduce DER, or do you want to get the rare speakers, or what do you want to do?
So it really depends on the final use case. If the final use case is a speaker attributed transcription, the main metric is speaker confusion. Okay. They don't really care about false alarm and misdetection because anyway they rely on ASR to take care of it. Okay. But for other use cases like the voice cloning, live translation stuff that I mentioned, misdetection and false alarm are the most important one. And it's okay if we confuse the speaker. So there are two very different families of use case where they are not interested with the same. So some of them will complain about speaker confusion, not being good enough. And some of them will complain about missed speech or not precise boundaries and stuff like that. Okay. So the two are important.
So then does that change how you train? Or?
For now, no, but definitely it will. Yeah, we're just getting started, so yeah, it will, probably.
Yeah. I had one more question, but I forgot, so I'll give the mic to someone else and remember it.
Hans Eyes.
Thank you for a very nice talk. So I was thinking diarization is like about human communication, about the meetings and debates and so on. Have you thought or have you seen requests for this kind of application from other maybe even non-audio domains? I was thinking, for example, about some production floor diagnostics where you have hum of some machines, then you have like some transport, then you have some people. And actually the people are into optimizing the processes or about detecting whether things go wrong or not. Maybe actually there can be even some stuff in biology, like you have different influences of different things on your body, and basically what you get is the mixed thing, and you want to come back to the different sources and when they got activated and when they were overlapping. So any other applications of this, like clustering / segmentation that you have seen?
Yeah, for now, we didn't have any customer coming to us with this in mind, but yes, indeed. It's just that maybe modeling what you are describing here as a clustering task might not be the best one. Sometimes you know the classes that you want to detect, so it can still be a classification task. I don't know, like sound event detection, like the decays challenge and everything. In the industry world, it might be more a better way to model the problem rather than, but yeah, it could be. Yeah.
Really interesting. So I actually have the other direction. How much of linguistics goes into these models? Because we all think about speaker characteristics as something, when we do diarization, it's the acoustics, but actually a lot of information is in who is talking about what. So we're working on doctor-patient conversations, and therefore, just by listening to reading through the text, you can basically always say, okay, this was said by the doctor, this was said by the patient, and so on, right? So how does this play a role in these approaches?
Right now we are as orthogonal as we can be to this kind of information. We really want to let's say, generalize to as many languages as possible, to generalize as many conversation characteristic as possible. So we want to be as orthogonal as possible, but indeed when you know, it's very useful. There are lots of work, even in the EMA group, trying to actually post-process the diarization or guide the diarization based on LLM on the transcription or stuff like that. But on our side, for now, we try to be as orthogonal as possible to the linguistic information.
And how do you do that?
Just by
using many tasks, I guess.
By training on as varied as possible the data set. It's more like a conceptual idea. We are not doing something specific to be, let's say, when we train a SSL model, we could try to kind of do adversarial loss to get rid of this information, but we don't, because I think it can still help, not at the semantic level, but locally it can still help to know that a speaker is using this phoneme rather than that one, and we let the model use it as it sees fit, but we don't, right now we don't do anything specific for this.
Yeah. And another question, since you have clinical in there, this is only a small number of recordings, but do you have statistics on these that you can share?
Do I have the what?
Yeah, I know, but they already did the work. Do you have statistics on turn taking or something like that? How many speakers, how long the pauses are, and so on?
How many speakers there are in this?
No, yeah, you do also voice activity detection and so on. I'm just curious if you have some statistics that you could share on the clinical portion of this data set.
Yeah, I would have to read the paper and go back to you, but yeah, I can point you to this.
Well, we can also read the paper, I guess. Yeah, thanks.
I think it's two speakers in each conversation, and we don't know how, if the same speaker is talking in several conversations. This we don't know. I don't think we do. Yeah.
Duration of turns or what?
Duration of turns, pauses between turns, and actually, if it's how real the recordings are too. Right? But that's probably something that's.
Are there others or? Yeah. So are these the ADOS interviews? The autism diagnostic study. Do you remember which clinical interviews these are?
I think.
Yeah. So these are for ADOS, the autism diagnosis something observer study. I can't remember. Yeah. So it's that set of interviews. It might not be typical of the kind of things you're working on this summer, which has to do with primary care physician visits. Yeah. Okay. I remember my question now. So this one actually doesn't make the point, namely that the error performance on things like restaurants or meetings is much worse than broadcast interviews. So if you go to one of the other ones where Andrew asked a question about the error bars. Yeah, this one, right? So I guess my question is, it looks like there's a huge variance. Maybe it's not that huge. I'm still thinking about it. But how much do you care in practice, like an industry, about the fact that you have goats and sheep, meaning on some files you do well and others you don't do well? Does that become an issue? Do you ever have any pressure to focus on the subset where things are not working well?
Yeah, no, not directly, but what I tend to do is when I fine-tune the model, tune the hyperparameters, I tend to optimize for the worst case rather than the average case. I don't know if that kind of answers your remark, or maybe I missed the point.
No, I think it does. It does. Yeah. Because I was remembering that, I call it the Joe Olive metric, but it was used once in one of the DARPA programs. It was for machine translation. And what the program manager said is, his name was Joe Olive. He said, I'm not interested in your average performance. I'll give you 100 files to translate. I'll look at the 90th percentile in terms of error. And then I want you to reduce that.
Yeah. So that's basically what I'm doing, optimizing for the worst 95% percentile or so, or 5%, whatever. Yeah.
Okay.
There's another one.
Outsider question: is there stochasticity in the outputs of these models? Okay.
There shouldn't be.
Okay. Yeah, I was just wondering if you can get on a bad path where you mess up early and then it gets in your context or something, but.
It might be because just of the GPU stochasticity, when they are hardware randomness, right? But it will probably rarely happen,
You mentioned in your introduction about live logging with glasses and so on. Have you done anything in this space?
No, not really. We do talk to a bunch of customers in this space, but usually it's not really speaker diarization that they're looking for. It's more like speaker tracking. So it's, I mean, it's a similar but different problem because it's a, you know, you provide a voice print of a speaker that you want to track, and the task is just binary task and like that. They, yeah.
And plus, you might have a visual input in addition, which can help many of the unknown problems that you have.
So in glasses, yes, but there are also lots of companies building, you know, what they call pendants or stuff, which is only a microphone and no video at all.
I see.
Where, yeah, you can't use that.
Yeah, Lucas, I'll give it to you. I just wanted to mention to Ramani, there's a law enforcement application which is exactly like this one. Very often the police obtain wiretaps to put in the microphone somewhere because they're interested in some bad guy. But then they don't want to listen to anybody else because that's usually against the law in most countries. So typically they then want somebody to listen to the whole thing before the investigators listen to anything.
Yeah.
And delete or cut out everybody who's not the target. And they've asked us for things like, you know, can you give us something where we just track the speaker in a 24-hour recording and we don't want to hear anybody else?
Yeah.
A question. So you mentioned you're running a company and at the same time updating an open source toolkit. And we can see on the benchmark that performances are a bit better when you use the licensed tool. How does it work in practice? When do you decide to integrate the private content into the open source toolkit?
We are still learning. It's a question that I'm asked a lot. Will you know, pyannote.audio open source evolve over time? It definitely will. Probably with tools around Pyannote, like I don't know. I'm about to release an interactive visualization tool of speaker diarization output, any tooling stuff that might be useful. And yes, at some point when our models, our current commercial model maybe we have a new one that is much better, we will consider, you know, putting that into the Pyannote open source world. So basically in the open source, there are two things. There are the actual toolkit and the pre-trained models, right? And right now, indeed, we don't have any pre-trained models that are actually easily shareable for now in the open source world. But the code, the part of the code to, I don't know, help, for instance, combining speaker diarization with transcription, with a lot of customers are asking for us. We will definitely open source this kind of code. You know, something that builds around speaker diarization and allows us to do a bit more than that. Yeah, but yeah, that's a question that we need to ask ourselves, and we are struggling to answer it for now. Yeah.
Okay. I have another small question. I don't know if it's been answered yet. How does it fare when you change the language? Because I tried to use Pyannote a few years ago with French, and it did not work so well. So do you do
when it
variations?
During a conversation, or?
No, I mean just regular usage, but without English.
So it's yeah, related to my answer about the linguistic information. It should be as orthogonal as possible to the language. We have as many languages as possible in the training set, and yeah, speaker diarization should be usually independent, agnostic to the language. Maybe what you witness is not a language mismatch, but rather the acoustic conditions that were different. So there are many reasons why it might have failed as well.
Okay, thanks.
Okay. Thank you very much. I do have Pyannote stickers. If you want to take one, feel free. They're here for that. Yeah, so I have the